Well, hello and welcome. Thank you for joining us. This is webinar number 14 of our Powerful Knowledge series, and today we're going to be talking all about reliability in power electronics. Reliability is actually a massive subject area with a lot of statistical and mathematical based approaches required. So today's 1 hour webinar is really just a high level overview of some of the key things that you need to think about in power electronics and some of the basics of reliability modeling. So I hope it's useful. My name is Ian Mosley. I'll be presenting today, and I'm joined on the call today with Jose Gonzalez, who's going to be looking after the questions and chat side of things. This is the 14th in our series. All of the previous webinars are available also on demand from our website. Perhaps Jose, you can put the link in the chat box for people to see where to access that from. This webinar will be about 1 hour long, and throughout the webinar, if you have any technical questions about the content we're presenting, please do take the chance to put that in the question box, which you should see on the right-hand side of your screen, and we'll have time at the end of today's webinar to discuss between ourselves some of those questions and hopefully provide a few answers as well. If you have any issues during the webinar, then on a more technical nature, please put those into the chat box, and Jose will do his best to facilitate any issues you have. And we'll also be launching some polls as we go through the webinar, just to give us a bit of a feel on the background of the audience today, just to give us background on your interests, whether you're into reliability modeling, whether that's something you actually do in your job. So I think that's probably everything. I will just bring up my slides and we'll get started. Okay, here we go. When I was writing this webinar, I thought it useful to identify just three key things that I thought it would be useful for you to take away from this webinar. So the three key things that I think are important for you to take away here. Firstly, how the basics of reliability and lifetime of power electronic systems can be modeled. And you can go into huge depth on this, but really, if you understand a few basics, you're off to a good start. So I'm going to show you some of that stuff today. Also, to understand some of the dominant mechanisms that you need to consider when designing and trying to quantify reliability and lifetime in power electronic systems, and what sort of things can cause failures. And I'll be finishing off with what I believe to be some good design practices, the sort of practical stuff that you should think about when you're trying to improve the reliability and performance of your converter from a lifetime perspective. So they're the three main things that we're trying to get across today. So the agenda itself, I'm going to start off with a few definitions of terms and areas you'll see used in reliability, so more on the definition side of things. Then I'm going to discuss how we can use or how we can model failure rates during normal operating life. So this gives you an idea on field failure rates and that sort of thing during a normal warranty period that you might find for a product. Then some thoughts on predicting end of life. The end of life is governed by different mechanisms to normal random failure. So you can actually use some methods to predict end of life. So I'll be going through some of that with some examples. The most common failure examples we've seen in practice, I'll just give you some pictures and some ideas on what we've seen over the years being the most dominant mechanisms in the sort of stuff we're working on, and then the good design practices at the end. So we'll kick off with a few definitions on reliability. So stick with me on this. This is really just an introduction to the sort of terms that you'll see being used. So the first thing is failure rate, and it's commonly denoted by lambda. And the failure rate is the mean number of failures for a field population in a given period of time. So if we had 1,000 units running continuously for a year and we had 10 failures, you could work out a failure rate lambda for that field population. So it generally relates to a field population, a large number of or a statistically significant number of items. You'll see quoted, the failure rate is normally quoted in something called failures in time, or FIT, and that is a term which is it actually stands for failures in time, and it's the number of failures per billion device hours, which seems a bit of a crazy metric to quote, but when you actually look into the reliability, particularly of modern semiconductor devices, they're incredibly reliable. So the number of failures you would get in terms of failures per billion device hours, you're probably talking a few tens at most, sometimes even less, of failures per billion device hours. So that's the metric that's typically used, certainly for semiconductor failure rate modeling. Mean time between failure, and this is actually very commonly misunderstood and misquoted in industry. Mean time between failure is not the expected lifetime or the expected duration a product is going to last for before failing. Mean time between failure is just another way of quoting the failure rate of that product field population during its normal operating life. And as you'll see in a minute, if you make the wrong assumption about what mean time between failure really means, you can be quite misled by what you expect your field population to deliver in terms of failure rates. And when lambda, the failure rate, is constant, you can quote the MTBF, mean time between failure, is just the reciprocal of lambda. There's another term called mean time to failure. So mean time between failure is a reliability metric based on items failing in the field and then being returned and returned to the field after being repaired. So essentially you have a fixed constant population of devices in the field. With mean time to failure, then when a device fails in the field, it's removed from the population. So gradually over time, your field population comes down. So there's slightly different ways of referring to how the system's used in practice or how it's modeled. So by far the most common is mean time between failure, which assumes this fixed constant field population. Okay, so I thought I would just grab some reliability data from a typical semiconductor. This is a step-down DC to DC converter, a typical semiconductor product. And you can get this sort of reliability data from pretty much most of the mainstream manufacturers. If you look up the reliability data, you start to see a few of the terms that I've mentioned already. So firstly, we have an MTBF figure. We have an FIT figure. So you can see here for this particular semiconductor part, the FIT figure is 0.5. So we're going to have 0.5 failures per billion device hours. So it's a very reliable part if it's used within its normal operating parameters. And there's some other data, though, here that we've not mentioned yet. There's a thing called usage temperature and confidence interval, confidence level, and activation energy. These extra terms become important because when you're trying, as a manufacturer, when you're trying to work out and quote the reliability data, you can't look at a whole field population. You have to look at a smaller, narrower subset which you can test in your factory and actually form an opinion about the field population based on an observation of a much smaller sample size. So that's why statistical modeling becomes important in reliability, because you have to base your assumptions about a behavior of a field population, so a huge number of parts, on the behavior of a small subset of that. And that's why things like confidence levels become important, as you'll see hopefully in a few slides' time. So the question is, how can we predict failure rate? And this comes back to a point I've just mentioned. So if you're a manufacturer producing semiconductors or whatever electronic part it is, you want to be able to give your customer some level of assurance on quality. So what you would do is you would perform typically highly accelerated live testing, because imagine if your product gives you an FIT figure of half an FIT, so half a failure per billion device hours. It's just impractical to try and quantify that in any other way than using some form of an accelerated test. So what we do here in most of the examples is you perform the testing of these devices at much higher temperatures, because higher temperatures, as you'll see later on, significantly start to increase the failure rate of your product. So the manufacturers will take a sample of products, put them into a highly accelerated live test, perform statistical analysis then on the outcome of that, and then provide data which then predicts the field behavior after that test. as I said before, though, you can only make those assumptions about the field behavior based on some level of statistical modeling, which includes confidence statements around your confidence in the data. And the more data you gather for longer, the more confident you can be in it. So essentially, there's a lot of statistical stuff that goes on in the background here. If we, for example, look at the data sheet of that part I just showed you on the previous slide, this manufacturer, you can actually represent the data they've presented in a sort of a friendlier format by saying, essentially, the manufacturer is claiming with 60% certainty that the MTBF is at least 1.96 times 10 to the 9 hours at 55 degrees C, which seems a very specific statement, but it's important in reliability modeling to include these certainty limits and the temperatures it's being quoted at, because if you're trying to benchmark what the quality of one manufacturer or one part against another, if you don't benchmark based on the same confidence levels or the same assumed operating temperature, you'll get vastly different MTBFs, which it may not be correct in terms of if you're trying to benchmark. So it's important to understand what certainty and confidence levels mean and operating temperature means, and how you can manipulate those to try and benchmark parts. You could, for example, with this particular manufacturer, they've used a 60% confidence level in terms of making their claim about MTBF. The same set of data, if they'd wanted to, they could have claimed a different MTBF with a much higher certainty level, maybe 90% certainty. But if they claimed it with 90% certainty at that temperature, they would have to claim a lower level of MTBF. So again, this is why certainty levels are important, because you can only make an assumption about a field population with a certain confidence level. And if you want to be really sure about something, you have to be less ambitious with the claim you make. So that gives you a little bit of context about how to benchmark the reliability of one manufacturer's part against another manufacturer's part. Now, if you, in practice, say we use this particular DC to DC converter on a board, maybe it's not running at 55 degrees C, maybe it's running at 80 degrees C or 85 degrees C. Obviously, the higher temperature you run it at, the reduced, you're going to get a reduction in MTBF or an increase in failure rate. So if you want to know the MTBF at a different temperature, most people, the best way to do that is to use something called the Arrhenius equation. And the Arrhenius equation is something that particularly came from studying chemical, or the rate of a chemical reaction, but it actually applies to semiconductors as well. And we'll show you in a few slides' time how you can use the Arrhenius relationship to actually normalize your MTBF or failure rates at different temperatures. And it's something that you commonly have to do when performing reliability modeling. So the bathtub curve, you may have come across this before. And this is a really key part of reliability modeling for a field population, because your failure rate of say you launch a product to market, your failure rate is going to be governed typically by three main regions. Firstly, when you first launch the product to market, you get something called infant mortality, whereby over time, for the first few weeks or months of operation, you have a failure rate which is decreasing. And what's really happening there is you're weeding out products which have been built incorrectly. So there might be a manufacturing issue or a bad connection or something like that. That's called infant mortality, because it's not a native quality problem necessarily that's impacting your normal behavior. It's a manufacturing problem. So what you tend to find is that manufacturers will put parts on a limited level of burn-in at the start before they release it to market. And that means then that you're essentially getting or weeding out the high failure rate that you might get for the field population before it actually goes out into the market. Once you've gone past the infant mortality region, you enter the normal operating life. And the normal operating life for a product is characterized by the failure rate lambda being roughly constant over time. And then at the end of life, you start to get different mechanisms coming in, and we're going to describe some of these later on. But at the end of life, the failure rate starts to increase because some aspect of the converter behavior, some aspect of one of the components has started to wear out or get used up, and it's like a non-recoverable degradation in behavior, and then that you can't do much about that. The product is end of life at that point. During the normal operating life, one thing that's really useful to do is you can use something called essentially the exponential probability distribution. So the probability during normal life, this only applies to normal life, the probability of the device surviving for a given amount of time can be expressed by this exponential distribution, which uses the lambda term. Remember, lambda is our constant failure rate during the normal operating life. Now, if you plot out, I've done this as a rather arbitrary figure. If we took an example of a lambda of 1/500, and that's a completely made up number, but it just made the maths and the graph work quite nicely here. If we had a lambda of 1/500 here, and we plot the probability of survival over time, so the probability of survival at time 0 is 1, because we're assuming all the products are working at time 0. Then as we start to progress through the normal operating life, there's a higher and higher probability of failure, or a reduced probability of survival. Now, I've actually highlighted one particular point on here, if you can see my mouse pointer, at the point whereby the time is equal to 500, which is 1 upon lambda. So this is actually the MTBF, the time equal to the MTBF. And this is something that's really important, and I hinted at this at the start of the presentation. You can see here the probability of a device surviving to a time equal to the quoted MTBF is only 37%. So by the time you get to a time equal to the MTBF in a field population, 63% of devices will have failed. Now that obviously is when you start looking at the maths, that all starts to stack up. But you can see why that causes a problem if you're making an assumption that the MTBF is actually the mean life of the product, because actually after that amount of time, 63% of your field population has failed. So hopefully that explains quite nicely what MTBF really is and how you have to use it carefully in terms of what you're using to predict about the field population. Okay, I think we'll launch question 1 there, please. Thank you. So we've covered briefly the normal operating life and how we can look at field failures in normal operating life. What happens then at end of life, and why is that different? So end of life, remember, is characterized by an increasing failure rate over time. And that's essentially what we're seeing there, is that there's some aspect of one of the components or multiple components in the power converter where some aspect of their makeup, if you like, is getting used up or permanently degraded to the point where the converter no longer operates in its required performance levels. So some good examples of that. Firstly, and this is by far the most common end of life mechanism for power electronics, would be electrolytic capacitors drying out. And I'm sure if you've worked in power electronics, I'm sure you've probably seen this happening. The problem with an electrolytic capacitor, obviously, is there's a liquid electrolyte inside the can of the capacitor. And over time, especially at high temperatures, if you're running this part at high temperatures, some of that electrolyte the pressure inside the can will increase, and some of the electrolyte will actually get forced out of the rubber bung that sits in the bottom of the capacitor to keep everything in. And as soon as electrolyte has left the main body of that capacitor, it can't get back in again. So over time, the capacitors dry out. And I've got some data a little bit later on to show you what happens exactly when these capacitors dry out. It can be quite catastrophic. But that's one of the key mechanisms that causes power supplies to fail, is electrolytic capacitors will dry out, and that causes end of life. One that I think we've discussed this on an earlier webinar when Jose was talking about packaging in semiconductor devices. But thermal cycling is something which causes real problems for power converters. And really what's happening with any sort of thermal cycling here is that you have, if you've got two materials joined together that have different coefficients of thermal expansion, and you thermally cycle, you get a mechanical stress on the interface between those devices. And as you cycle that backwards and forwards, over time, it just weakens that interface. And this picture here is an example of what can happen to a bond wire in a semiconductor due to thermal cycling. And you actually get the bond wire lifting off the semiconductor surface, and then over time, it'll be a bad connection, or it might be no connection at all, and the device stops working. So thermal cycling is something which is bad for semiconductor bond wires, but also it causes other problems, as we'll see later on with certain types of ceramic capacitors. You have to be a bit careful as well. Oops. Some other part, this is often overlooked, surge suppressors, so things like metal oxide varistors that are used on the front end of a power supply to protect against aggressive surge levels coming in. When you actually look at the crystalline structure of those parts, it's almost like lots of individual miniature MOVs all in parallel with lots of crystal barriers there. And what happens is when a surge comes along, the energy is dissipated across all of those individual tiny little MOV type structures inside the main MOV. And over time, if you hit them enough time, that some of them start to get degraded to the point where they can no longer clamp. So you get this gradual degradation in the ability of the overall MOV to clamp surge voltages. And after a certain number of hits of high energy surges, either the device will fail completely, or it will clamp at such a high voltage level that the downstream circuitry gets damaged. So that's a long-term wear-out mechanism, because this crystalline structure is something which changes permanently each time you hit it with a surge event. Connectors. Depends on what type of connector you use. The example here is actually a high reliability connector, but any connector will degrade each time it's connected and disconnected. And they have a specified number of mating cycles. Over time, if you mate and then disconnect the connector too many times, the contact resistance will increase. And if you're conducting power through that, obviously then the contacts start to get hot, or they might break. So connectors can be a reliability issue as well. And this particular one, I think, has got 10,000 mating cycles, and it's using gold plating as well to manage the connection and the reliability. So it depends on which one you choose. But if be careful with connectors, because they can be a weak point in a system. Okay. Electrolytic caps. You'll see throughout the course of this webinar that I keep mentioning electrolytic caps, and it's for good reason. It's because electrolytic caps, in my experience, are one of the weakest points you'll find in any power converter system. And we've seen failures from multiple different pieces of equipment we've been asked to take a look at, and nearly always it's electrolytics that are causing the problem. So I thought I'd just put up some of the some details about how you can go about, or how end of life is how end of life is considered for electrolytic caps. And I'm using data here from Rubicon, which are actually very high quality parts. So this is just treat this as generic data, really. We tend to use high quality caps if possible, because otherwise you get reliability issues. The first thing to state is that the capacitance you'll see quoted on the data sheet is typically has a 20% tolerance. Even just at start of life, you'll only be within plus or minus 20% of the target specified value. And the ESR of that capacitor is that's determined actually by something called the dissipation factor. So dissipation factor tends to be quoted on the data sheets rather than ESR, but they are related by this equation. F in this case is 120 hertz. So you can work out ESR. And end of life, at least the way it's defined on these data sheets here, is when the capacitance has changed by more than 25% of its starting value, or the dissipation factor, which essentially is the ESR, increases by more than 200%, or the leakage current in that capacitor exceeds the datasheet specification. So that's how the manufacturer will essentially say this part has now reached end of life. But let's take a look at that. What does that really mean for our design? If we take a look at, this is just an example part here from this data sheet. It's a 470 microfarad, 100 volt electrolytic cap. So you can see I've marked the curves here as being capacitance on the x-axis and ESR, or you could think of it as dissipation factor, but I've put it as ESR here on the y-axis. So at the start of our life of our component, let's assume we've got a nominal 470 volt, 470 microfarad component. Well, it could have plus or minus 20% tolerance on its capacitance. So the orangey yellow line here is the area in which we expect the initial component as it comes out off the manufacturing line to sit. So it's going to sit somewhere within this orange box in terms of capacitance and ESR. Now, remember the data sheet is saying that at end of life, the capacitance changes by up to 25%, or the dissipation factor can increase by a factor of 2. So if we now plot out what that might mean in terms of the capacitance and ESR window that we might expect this part to sit in, you can see here that actually that starts to become quite a wide window. Now, it's very unlikely as a part ages that your capacitance is going to increase or your ESR is going to go down. So you tend to see, as the part ages, a shift to the left and up in terms of ESR. But theoretically, you could sit anywhere within this blue window at end of life. And why is it important we think about that? Well, firstly, in this particular case, if we use the factors that are given in the data sheet, the capacitance for that part could vary at end of life anywhere from 282 microfarads up to 705 microfarads. It won't go up, but I've included that as a limit here. And the ESR could be anything up to about 0.45 ohms. It's generally, you're not going to have 0 ohms, so you tend to see the ESR increasing over time. Now, why is that a problem? Well, from a manufacturer's perspective, so you're building it into a power converter, imagine if you're having to deal with a part which only at end of life could have a capacitance which is over such a wide range and an ESR over such a wide range. At end of life, the impact on your converter, the output ripple could increase significantly, but the part is still effectively still good, or just about good. But also, if you've designed a control loop which has dominant behavior, which is impacted by either the capacitor value or the ESR, you could have issues with stability, that you could have a power supply going unstable towards end of life, but the capacitor actually is still technically a good part. So that's why when you're designing things like the control loop, you need to have very good stability, gain and phase margin built into the system, because of this sort of variation you might get in an electrolytic cap. Now, here's a nice little graph for you. This is some data we captured a few years ago. Now, note these are not Rubicon parts. I haven't put the manufacturer up here. These were parts that were taken from equipment that was already aged. And what we did is we took the parts out and we measured their capacitance and ESR. We then put them into a thermal chamber and aged them for a certain amount of time, just to see what happened as we performed a sort of a higher temperature accelerated aging process on them. So you can see here the blue diamond shapes are the initial values, and then the cross shapes here that you can see are then the ESR and capacitance combinations of the aged parts. What you're really seeing here is that due to the extra aging we put onto these parts, you start to see electrolyte loss, which causes the capacitance to go down and the ESR to go up. So you start to see the parts move in roughly where this arrow is. That tells you roughly what's going on as the parts age. And the trouble is also when particularly if your ESR starts to increase, remember an electrolytic capacitor in a power electronic converter may be handling quite a high ripple current. If your ESR starts to increase, then the heating effects, the self-heating effects inside the can of the capacitor will start to increase. So the part gets hotter, which means it loses more electrolyte, which means we get more degradation. And essentially, after a certain amount of time, the system just essentially thermally runs away. You get no good behavior at all, and it just fails. So that's what's going on when electrolytic caps dry out, and it's why you need to choose high quality parts and be careful how hot they get during normal operating life. So we could launch question 2, please, there. Thank you. So if you look into the data in fact, the Rubicon data sheet gives you this, you can see that the basic equation governing lifetime is given by this expression that you can see on the slide. Now, what their state is, when you actually look at that, what they're really saying is that for every 10 degrees C drop in temperature, you get a doubling of the lifetime of the component. So that sounds great. That's how we can actually choose a part and derate its temperature to make sure it lasts for how long we need it to last for. So if we take a look, for example, on the previous datasheet parts, I think they were 10,000 hour, 105 degrees C rated electrolytics. If we then plot out lifetime as a function of temperature as we back off from 105 degrees C, you can see here that each 10 degrees C drop, we double the lifetime. So going from 105 degrees C to 95 degrees C, we go from 10,000 hours to 20,000 hours. If we go from 95 degrees C to 85 degrees C, we go from 20,000 hours to 40,000 hours. So you start to see the impact that temperature has quite quickly in this sort of a relationship. If, for example, we were designing a product to last for 10 years and we were using this part, well, we want to make sure that that part was not operating at more than 74, 75 degrees C during its lifetime, and then it should last about 10 years. The only thing, though, is you have to be careful also with electrolytic caps not to exceed their ripple current rating, because not only will they be heated by the environment they're sitting in, if they're, for example, an electrolytic on the output of a flyback converter, it might have a lot of ripple current in it, and that causes self-heating inside the capacitor. So firstly, you mustn't exceed the rated ripple current of the part, but you must also include the ripple current self-heating effects when you're looking at temperature and derating using these curves. There are more detailed models in the literature, and I think I've got an example. Yeah, this is taken from that data sheet of the that's provided by Rubicon. So you can see in this case here, we've got the basic lifetime equation, which is the same as what I put at the top of the slide. There's actually then a factor, and this is including the effects of self-heating. So TS here is the surface temperature of the electrolytic capacitor, and this TJ, that's actually the temperature inside the core due to the I²R losses due to the ESR. So there's an adjustment factor here that is essentially modeling the additional temperature due to the ripple current it's supporting. And there's also a component here, VR upon VA. What that's modeling is the fact that when you have a DC bias across an electrolytic capacitor, you have a small amount of leakage current flowing through it, and that leakage current essentially causes a consumption of the liquid electrolyte. So you get a degradation in the electrolyte inside the capacitor due to the leakage current, and that's what that third term in this equation is modeling. So it depends. If you want to get a rough idea on lifetime, just use the first term here. That gives you a rough ballpark of what you need to be looking at for a lifetime rating. If you really want to get into the detail, you need to start modeling the other effects as well, though. Right. Okay. Reliability modeling. The best way I thought to describe this is to give an example of an AC to DC power supply, something you might find being used very commonly. And again, good manufacturers will provide plenty of data about reliability. So this is the data sheet that I pulled off for this particular power supply here. They're saying, well, in fact, for our example here, let's consider a field population of quite a high population, 100,000 units running in the field 24 hours a day and 365 days a year, so running constantly, and the local ambient, let's say it's 30 degrees C. How can we work out the number of expected failures per year during normal operating life? Well, if we look down to the quoted MTBF data given by the manufacturer, that gives us a good starting point because we've got quoted data here at different temperatures. We'll use the one for 30 degrees C ambient. So the probability of a single unit failing in 1 year, this is governed by that exponential relationship and the failure rate I've spoken about before. And because we're in the normal operating window of the failure rate curve, we can relate failure rate and MTBF. They're essentially reciprocal of one another. So the probability of failure is given by this expression here. So in our case, time t it has to be put into hours. So 24 hours times 365 days. So that's how many hours there are in a year. And on the bottom line, we've got the MTBF. So the probability of a single power supply failing in 1 year is 0.2441%. So very low probability. But remember, we've got 100,000 units in the field. So we need to multiply that out by the number of units we've got. And therefore, we would expect, under those conditions, based on the manufacturer's data, about 244 of those power supplies to fail every year. And based on a field population of 100,000 units, that's not too bad. That's actually a reasonable MTBF. It's a fairly high quality power supply. However, look at what happens if the ambient temperature now increases to 50 degrees C. We can do the same calculation here. I mean, we could use the Arenas model that I've spoken about, but actually, we've actually got quoted data here for 50 degrees C. We can use that, and we expect 533 now to fail per year. So as you might expect, as you go up in temperature, you're going to have a higher failure rate, so you have more of your field population failing in that given 1 year period. So that's just a simple way to model field failure rates during normal operating life. However, if we want to now start looking at the behavior of your failure rates with temperature, really the failure rates, you need to model them using this Arenas equation. And I've mentioned this a few times, so I'm going to put it up now and show you what the Arenas equation really looks like. So in the context of reliability modeling, you have this thing called the acceleration factor. And what it's predicting is how much the failure rate of a system will increase when you change between two different temperatures. There's a few variables in here that I'll briefly discuss. Firstly, EA is something called the activation energy, and in this equation here, it's quoted in joules, but sometimes people also quote it in electron volts. It's you can go between the two using the fact that 1 electron volt is given by 1.6 times 10 to the minus 19 joules. And the activation energy is, again, something that sort of comes from the world of chemical processes. It's the minimum amount of energy to make a chemical process work. In the case of semiconductors, it's the minimum amount of energy to make the semiconductor operate, if you like. I think I've got some data in a minute which gives you typical values for this. Yes, so the activation energy in terms of electronic components will vary from one component to another. For semiconductor devices, values of 0.7 electron volts are fairly typical for semiconductors, and that's often used as almost like a default in the industry, but you will have slight changes and differences between different component types. The value K is Boltzmann's constant, and then the temperatures T1 and T2. They're just the temperature, but it has to be temperature in Kelvin here. If you make an assumption that the activation energy is 0.7 electron volts, then you can come up with a fairly useful approximation to the Arenas relationship here. And this is where the data that I showed you on the previous slides comes from. If you use about 0.7 electron volts and assume just a 10 degrees C delta in temperature, you can show that this equation gives you roughly an acceleration factor of about 2. And that's exactly what we saw in the previous slides. And what I've done here is actually to plot out. So imagine, probably the best way to describe this, imagine the first temperature being, say, 40 degrees C. What I've done is to calculate the acceleration factor from 40 degrees C to 50 degrees C with an activation energy of 0.7 and plotted that here. And the reason I've done that is that if you assume your power electronic system is operating over a temperature range of maybe typical room temperatures or operating temperatures might be about 20 or 30 degrees C up to about 80 or 90 degrees C, which is fairly common, then you can see we're not far away from having a factor of 2 for acceleration factor. And it's much easier for people to keep that factor of 2 in mind. So a factor of 2 for every 10 degrees C change is quite a nice thing to remember, rather than this whole Arrhenius equation. So that's where it comes from, and it's reasonably valid. But just keep in mind that it's only ever an approximation to the Arrhenius equation here. Okay, we'll launch question 3 there, please, Jose. So standards, obviously when you start involving statistical analysis, you have to be a bit careful, because you can pretty much make statistics say whatever you want them to say if you use them in the right way. So therefore, some level of standardization is required in terms of if you're going to compare reliability data from one manufacturer to another. One of the oldest standards, it's rather out of date now, and you can see that from the picture here, is one of the mill standards. So mill standard, or the mill handbook 217F. You can actually get a copy of that free online now. It's publicly available, but it is somewhat out of date. But that's very commonly quoted for reliability prediction. And what they do is that is quite a big document. They give you the background reliability data for almost like a macro model of a particular device type, like a transistor, a resistor, a diode, with various different factors in there to try and give you, to include different use cases for this part. So, for example, if we look under the mill standard for the reliability modeling of an N-channel silicon FET, so this is under 400 megahertz, you end up getting this equation here that you can see where my mouse pointer is, where we have a failure rate lambda. So that's the same failure rate that we've previously described. But here it's formed from a base failure rate, which in this case here is different whether it's a MOSFET or a JFET. And I have no idea where they get that data from, but they have a base rate there that depends on the transistor type. You then have these factors, these pi factors. So pi t is accounting for temperature. So that's a bit like the Arrhenius relationship we spoke about before. You have an application factor, a pi a factor. And that, in this case, the way they treat this is that they differentiate between it being a linear amplifier or small signal switching, will give different acceleration factors, essentially. That's what the pi a models. Pi q is a quality factor, and I think that models the quality of the supplier providing the information to you and their whole quality process. So there's a quality factor there, and then there's an environment factor. The environment factor in the case, again, this is coming from the military spec. You have GB, which is ground benign, and that would be something at ground level in a very nice, calm environment, all the way through to very aggressive environments, high vibration and stress, shock loading, all sorts of stuff. And they factor that into the environment here. So that's one way of looking at reliability. But I would say the mill standard approach is something that's much less quoted now. Let me just whiz through. I've already mentioned those. Far more commonly quoted these days from manufacturers of electronic components is the Telcordia standard SR322, and that is I guess a more up-to-date and relevant way of looking at reliability prediction. You have to actually pay for a copy of that one, though it's not publicly available, but it goes into the whole detail of how to predict reliability and standardized ways of quoting data. So it's quite good if you're looking at trying to quote reliability data. This is a good standard to refer to, because then people know what you're talking about. So we're coming on to some common failure mechanisms now. As I mentioned earlier in this webinar, one of the main problems with thermal cycling is you have this different coefficient of thermal expansion, and that leads to repeated mechanical stress with thermal cycling. So the sort of things that causes are fractures in components, broken connections, and degraded thermal conductivity. I showed you a picture of a bond wire earlier. If we look at this, this is actually an image of a BGA device, a section through a connection on a BGA device. So the slightly darker grey area is the metal of the semiconductor package, and then this lighter grey is the solder ball that sits underneath it. So over time, you can see at the start with 0 thermal cycles, we've got a pretty good looking connection there. As we start to thermally cycle, you start to see cracks and fissures start forming between in the solder joint here. And as we continually thermally cycle, those cracks get worse. And over time, you can imagine here that this connection might become intermittent, broken, and cause all sorts of problems. So that's another good example of what's happening with thermal cycling. Ceramic capacitors I mentioned earlier. So ceramic capacitors, pretty much by definition, are made of ceramic, which is a hard, brittle material. And if they're just directly soldered onto a PCB, onto solder pads, then if the PCB material has a different CTE compared to the ceramic, which it probably does, then thermal cycling is going to put stress on the body of the ceramic capacitor, and over time it might crack and then short out. And that's particularly a problem for some of the larger case sizes of ceramic capacitors. So if you're designing for a high reliability system whereby you need ceramic capacitors and you're subject to a lot of thermal cycling, you might want to consider some of these alternative structured ceramic caps whereby they have a lead frame around them now, which gives them a far greater degree of mechanical flexibility to soak up some of that mechanical stress and not impose it directly on the ceramic material. And these sorts of packages are very often used in oil and gas applications or other high rel applications as well, to avoid capacitors cracking. Automotive is also something whereby the ceramic caps are exposed to fairly high thermal cycles and repeated thermal cycles. So some manufacturers have developed, this one's called FlexiTherm. They've developed different ways of forming their ceramic to give more mechanical compliance to the structure, so that thermal cycling doesn't cause the sort of failures that you would otherwise see. So again, if you're worried about ceramic caps, there are alternatives out there that could start to deal with some of those reliability issues. Surface contaminants. This is I've not mentioned this so far, but if you're using forced air cooling to cool your power electronics, then you're going to be sucking air in from some external ambient. You might have a filter in there, but the filter you'll still get some level of dirt and contaminant getting into your system, and also moisture. If your moisture is getting into your system, that can cause problems when it settles on a surface of a circuit board as well. And the problems that causes, especially in systems where you've got high voltages present, is if that dirt and dust at a certain point starts to become conductive, then at a certain point you might start to get some current flow between those high voltage traces. And if that current flow is high enough, it can cause heating, and then you develop an arc. And then if you start getting arcing in your system, well, it's pretty catastrophic. And we've seen it on systems in the past as well. And it's the energy levels contained in arcs are just huge. They just vaporize everything. It's a very destructive thing to happen to a circuit board. And when that arcing happens, it vaporizes the conductor metal that the arc is formed between, and then deposits that vaporized metal over the surface of everything nearby it. So once you get arcing formed, it then is going to create more opportunities for arcing as well, because of this deposit of metal conductor around the arc itself. So it's a very rapid and catastrophic failure that you'll see there, and pretty much unrecoverable. So what can you do to get around that? And we've done this sort of stuff in the past. If you are concerned about contaminants getting into your system, then essentially you just need to use good design practices that you might use for a high pollution degree environment. And really, that's just about creepage and clearance. You have to have good spacing between your traces. You might want to put slots in the board between those traces as well, because if you put a slot in a board, obviously you can't get tracking over the surface. Or commonly you can use PCB conformal coating. So in that case, essentially you put a thin liquid layer of a material which sets to create this impervious barrier over your PCB, and just really inhibits the opportunity for arcing to occur between traces. Obviously, it costs to do that, but in a high pollution degree environment or a high moisture environment, conformal coating can really significantly improve your reliability of your system. ESD and surge, I thought I'd put up here. It's debatable whether you really call these reliability events or not, but it's something which kills electronics, so I thought I'd mention it. So ESD, electrostatic discharge, is something whereby you have a high energy but very short-term surge into your system, and the sorts of things that get damaged by that are high-speed digital circuits, and because a high-speed digital circuit has to have very low capacitance on its input, it means it's much more susceptible to being damaged by ESD. Or something we test for here fairly regularly is the sort of effects of lightning strike on a mains power supply. So the CWG surge, governed by 61000-4-5, is modeling a lightning strike on power lines nearby to your power supply, and some of that energy can propagate into the front end of your converter and cause a lot of problems. So there's a lot of energy behind these surges, and you need to put some level of surge protection on there to make sure your power supply is not damaged. Another one that can cause mischief in any power converter, particularly if you've got a digital control system, are electrical fast transients. These are fairly low energy transients, I would say, certainly compared to the lightning surge, but they're characterized by having very rapid very rapid rising edges. So if you inject these sorts of surges onto, say, a wiring loom, they can cause havoc with digital circuits because they create noise everywhere, and it can cause all sorts of problems, the system to latch up, and other sorts of effects as well. So those are the main surge events that you need to watch out for when designing your system, and you should certainly be testing your system with these sorts of surge events just to make sure that you can ride through and survive them in a good manner. So we'll launch question 4 there, please, Jose. This is a fun one. I really like this picture. It's something we put in our white paper. It's something called dendritic growth, which sounds quite a nasty sort of thing. But essentially, if you have a printed circuit board whereby some contaminant, a liquid contaminant or moisture in the air, gets deposited onto the surface of that circuit board, it provides a material through which ionic or electromigration can happen. And electromigration is the flow of metallic ions from one point to another. So if you've got voltage between those 2 points and moisture between them, then you tend to get this electromigration effect. And what happens over time, it's quite a slow process, but you get these little feathery whiskers forming between the two nets. And if enough of them form, obviously you're starting to create a higher and higher leakage current. At a certain point, it creates a short circuit, and that's obviously pretty catastrophic for your system. So normally that's due to some sort of surface contaminant, like water, normally something like that. Increasing the temperature your system is operating in, it goes back to the Arrhenius law again. So dendritic growth essentially is an electrochemical process. So increasing the temperature your power supply is operating in will cause that process to happen at a higher rate, and therefore dendrites will grow faster, and your lifetime of your product will reduce accordingly. The only real way to get around that, again, is moving back to things like increased creepage and clearance, like we discussed before, or using conformal coating again on your PCB. Conformal coating is very often used in automotive power electronic systems because there's moisture around in the air, and they just need to be highly reliable. So conformal coating is a way to avoid this sort of dendritic growth, and it's something that's certainly to be aware of. One other point, I put this point in just at the end of preparing this presentation, because a very similar mechanism is one of the main reasons that the early days lithium-ion batteries had problems. So in a lithium-ion battery, you can get these little dendrites forming. In fact, they always do form. I don't know if it's the anode or the cathode, I can't remember which. But you get these dendrites forming, these little stalactite type things. And the first effect they have is they degrade battery capacity, which we know that batteries degrade over time. But if you're really working your battery incredibly hard, i.e. your battery's getting hot, then the same effect occurs, but it just happens faster due to the Arrhenius relationship. And if those dendrites grow fast enough, they can actually punch through the film that separates the anode and cathode in the, or separates the structures of the lithium-ion battery. And if that happens, you get a short in your battery, and that's what caused battery fires in some of those early lithium-ion parts. So if you're interested, perhaps have a look after the webinar on dendritic growth in lithium-ion batteries, because there can be a catastrophic effect that happens and kills batteries quite quickly. It's far less common now, though. So briefly, good design practices is really just how do we avoid the vast majority of what I've described so far in the webinar. So firstly and key is try to avoid excessive component temperature variations. That temperature is the thing that will kill power electronics, and variations in temperatures. So try to avoid excessive component temperatures. If you do need high reliability, you might want to look at components that are specifically designed for high reliability, like flexi-term caps, or those ones I showed you whereby the ceramic caps are on those little lead frames. That can certainly help. I've put a thermal image here. Be careful when using electrolytic capacitors, though. I guess it's just default now, I always avoid using 85 degrees C rated parts. So 105 degrees C parts are really a minimum for any power electronic system. Sorry, the reason I put a thermal image there is when you're doing your thermal assessment, I've mentioned a few times you need to look at component temperatures, and there's a number of ways of doing that. So if you use thermocouples to look at component temperatures, we do that. It's a great thing to do, but you only tend to put thermocouples onto devices that you expect to get hot, because you have a limited number of channels. And it's quite hard. You can't really put a thermocouple on a little tiny 0603 resistor, for example. So I would suggest always using thermal imaging of your power converter, because you don't know if you've made a design mistake. Maybe you've misdesigned a snubber in your power stage, and your snubber resistor is burning up. You might not know, if you don't use a thermal image, you might not know that that's happening. And if therefore your snubber resistor just fails, maybe a few months into operation of your power converter, well, what will happen then is if it's a snubber resistor at least, is your EMI might go up, or you might start seeing excessive voltage, which will degrade the diode or the MOSFET that your snubber is connected across. So it can cause a secondary failure. So using thermal imaging is a great way to sanity check your design and make sure that you haven't got some tiny, tiny little obscure little component that is going to fail quickly and have a knock-on impact onto your reliability of your system. And definitely using enhanced creepage and clearance and conformal coating for high pollution environments is a very good way to increase the reliability of those systems, and something that's definitely worth considering. So we'll launch question 5 there, please, Jose. Thank you. And we're nearly done now. So good design practices too. And this is all a bit arm-waving statements, but I'll try and justify them. Firstly, don't run your magnetics. If you're designing your own magnetic components, don't design to run them too near saturation, because as soon as you saturate a component, its inductance drops off a cliff, and therefore your currents will rise quickly and you can start getting failures quite quickly. And also, you would never normally design them to run at any temperature near to Curie, but be careful. If you've got a little ferrite core buried in the depths of your system and it's getting anywhere near Curie temperature, if it goes through Curie, its magnetic properties will disappear and it becomes like an air-cooled inductor, and your current will take off again. So typically, we're fairly conservative with how we spec maximum flux density. Probably about 300 millitesla is about what we feel happy with. Sometimes we push a little bit harder, but very rarely. And yeah, I mean, you can't really run anywhere near Curie anyway. So make sure you satisfy that for magnetics. This is a point, a slightly more subtle point, for if you're designing a power converter that's powering digital circuitry, you really want to try and design the voltage rise of that power converter to be monotonic. And by monotonic, what I mean is that when it powers up, the voltage increases at a constant rate, and then when it reaches the regulated point, it doesn't overshoot, it just levels out and flattens. It doesn't come down again. And the danger if you don't do that is if your power supply starts up aggressively and overshoots the output voltage and comes back down, with a digital circuit, if it sees that power, at a certain point it's going to come out of its power on reset. But if the voltage dips down again, it might not behave very well. It depends how the power on reset circuit is working. It can put it into an unknown state. So you really want a nice monotonic startup, a nice soft start controlled system with a nice monotonic startup will mean that your digital circuits you're powering can do their job properly. We always tend to put differential and common mode surge protection on power supply inputs for meeting the requirements of lightning surge. It just gives you a more robust product. And ESD protection on digital inputs is pretty much a must as well, especially if you've got connectors that you can touch quite easily going out to the rest of the system. Always use soft start, otherwise your power converter is subjected to a horrible transient condition when it first starts up, which can lead to cause saturating and other effects. So again, measure that once you've built your converter to make sure it is giving you a proper nice soft start behavior. And again, then you can, once you become familiar with reliability modeling, you can perform your own highly accelerated live test on your product, which will give you a baseline of reliability data, but it will also start, if you perform highly accelerated live testing, it also will start to highlight any components or any parts of your design which might be need attention. So any weak spots, for example, will be highlighted at a nice early stage when you can decide whether you want to do something about that or not. And again, you can use production burn-in to reduce infant mortality. That prevents field returns as well. And above all else, really, I'd recommend using component suppliers who do give proper reliability data and quote confidence levels and all that sort of stuff. It gives you an idea that they're managing the proper quality process behind their manufacturing. And that's something that's quite important if you want to have a good quality product. So I'll just finish off. This is the last slide now. So recommended further reading. As you'll appreciate, today's webinar really has been a high-level introduction to some of the common aspects of reliability modeling. When you really start getting into it, I think the image I've shown on the screen here is the latest edition, but we've got the older one here. You can see you start getting into a lot of detail. If you're really interested into reliability engineering, you might want to take a look at getting one of these texts, which they describe all the sort of statistical approaches that you might need to follow to predict reliability in your system. And there's obviously it's a huge amount of information, but it's worth getting into if you're really serious about having high quality design. And I thought I'd put this one up again. The same theme. I keep referring back to electrolytic caps, and for good reason. There's a really nice application note written by Rubicon, which you can access from this link. And it gives you a lot of the detail that I've described in earlier slides, how you can go about modeling the lifetime of their capacitors based on temperature rise of the can, based on voltage derating and all sorts of other bits and pieces, frequency coefficients, all sorts of things. And it's a really good short couple of pages that is always worth having to hand when you're looking at modeling the reliability of electrolytics. So maybe take a look at that as well. Oops. And that's it. Hopefully that's been an interesting overview for you all in reliability modeling, and we can open up for a few questions now. Let's see what we've got. Okay, good. We've got some questions here. So firstly, we have seen firstly, thank you for the questions. We have seen relationships that connect steady state temperature with component reliability. Is there anything like that for temperature cycling? Oh, that's a great question. We ran this webinar this morning and we had pretty much exactly the same question. Probably Jose, you might want to comment on that.
Yeah, so we covered that in the previous webinar regarding power cycling. So if you haven't attended, you can watch that on demand. You can check the link, and yeah, the temperature affects the lifetime. So if you increase your case temperature, your low temperature, your number of cycles to failure is going to decrease. So that's both for the Lesit power cycling model, and both for the SIPS 2008 model. So you can check that in the previous webinar regarding power cycling. I think it was 2 webinars ago.
Yes, that's right. So I'm just looking on our board. That was your presentation, Jose, on packaging of power semiconductors, which I've made a note here was webinar number 11. So if you didn't register for that one, Jose, have you put the link up to our website where people can access?
Yeah, that's on the chat.
Okay, so if you follow that link to our website, you should see webinar number 11, and Jose does a great job on describing some of the stuff you're asking about there. So thank you for that question. That's a very important point.
Also, I'm going to put the book that I shared in the morning.
Oh, great. Yeah,
So,
thank you. Then the next question, what is the value of typical activation energy for electrolytic capacitors, or MLCCs? The honest answer is I don't know. That's a very good question. I tend to assume similar activation energies as semiconductors, but that's probably not completely accurate. If you find out, maybe let us know. I'll have to have a look around myself as well. For semiconductor, there's a lot of reliability data for predicting failure rates, but for semiconductors, and for capacitors and sort of passive devices, people just don't seem to have the same amount of data there. So the bottom line is I don't know the answer to that. I'd like to know. Yeah, I'm sorry I can't answer that anymore, but a very good question. I don't know if there are any other points, Jose, you wanted to bring up during the course of the presentation.
I will probably just say that things have changed a lot since the emergence of wide bandgap power semiconductors. So things have to be reanalyzed again. Before, everything was silicon, and now you have silicon carbide, gallium nitride, and a lot of assumptions, they have to be changed. People, they are still studying the materials, and JEDEC, they have a committee that is studying that on how reliability modeling will apply.
Ah, okay. Do you think on that point, with wide bandgap devices obviously have by definition a wider bandgap, would that have an impact on the activation energy as well? Are they related?
I cannot comment on that. I mean, mainly now people are focusing on the trapping mechanisms and transient effects that were not present on silicon devices. But regarding that, the first guess, it would say yes, it should be different. But again, you need a lot of data, you need a lot of experiments, and again, would you like? Imagine that you are a manufacturer. Would you like to wait 10, 20 years for having enough data to release your product? So I think that's a tricky question there.
Yeah, it's a very good question, but a tricky one. All right. I think we don't have any other questions for now. So I'd like to say thank you very much for joining us today. It's been a pleasure to have you here. I hope the content has been interesting and useful, and we hope to see you on a future webinar. Thanks very much.
Bye.